Hi everyone, my name is Elyse and my partner is Nadeem, and today we are going to be talking about the synthesis of Lagevrio. So in this presentation, we are going to be going over the background reaction process, mechanism, and method of this medication. So what is Lagevrio? It is an antiviral medication used to treat COVID-19 symptoms. It is a prescription-only medication for the ages 18 and older to prevent progressive symptoms when testing positive. Doctors are prescribing it as 4 capsules taken by mouth twice a day for 5 days, and it is a total of 40 capsules. It is important to note that it is only authorized by the FDA for emergency use authorization, so it's not actually FDA approved. Its generic name is Molnupiravir, and it is manufactured by Merck & Co. So what are the benefits of taking this medication? Clinical trials have shown that Lagevrio is associated with risk reduction of 30% in hospitalizations or death. It has shown consistent data with high-risk patients. High-risk patients being those who are ages 65 and older or those who have immunocompromising diseases. Disadvantages of taking Lagevrio is that it is not FDA approved and it is only authorized for emergency use. It should not be taken during pregnancy or breastfeeding. The FDA actually prefers Paxlovid to be taken as it has gotten the full FDA approval. So how is Lagevrio made? The synthesis of molnupiravir is actually from uridine, which can be made from ribose. The process requires a minimum of 3 transformation steps: acetylation of the primary alcohol, nucleobase installation, and the installation of the oxen. These transformations can actually be performed out of order, but the stability of intermediates must be taken into consideration. Different orders of the transformations were taken in an attempt to obtain a higher yield. The current process is 70% shorter than the original proposed route and provides a much greater experimental yield.
So this is the way to make Lagevrio, or the patented version at least. So you can see you use uridine and you eventually make your way to the final product of Lagevrio. And it's done through these chemical processes, but the problem is it takes a while and it has a 17% yield, which is pretty bad. So the new patented version is just a simple reordering of the reactions. So the same reactions are being done just in a different order and slightly different reactants. So a benefit of this is it actually increases your yield by threefold, going from 17% to 61%, and it actually occurs faster. And then just the way it's reordered just allows things like the deep protection of this acetonitrile to just go faster and more smoothly, have a higher yield. So step 1 is triazolation. It's when you add this 1,2,4 triazole group onto this carbonyl. This is done where the lone pairs will do backside attack, kick up the lone pairs to the oxygen. This oxygen will then be grabbed and taken off, and then you'll be left with final product after a elimination of this hydrogen to form a double bond. Next is acetonitrile protection. So these OH groups need to be protected, or else you can't add any acid or bases later on. So the way this is done is by adding acetone and a strong acid. So this will happen where the strong acid will protonate the acetone, becomes a better leaving group, where the electrons will be more likely to go up to the oxygen when it does attack. And then you're left with this protonated oxygen, which needs to be deprotonated by the acid. This OH at the very bottom then needs to be protonated in order to make it a good enough leaving group for these lone pairs to kick it off, giving you a H2O as a byproduct. These other lone pairs on the other OH will do backside attack on this carbonyl, leaving you with a cyclic ester of sorts. This hydrogen will be then taken off by a bulky base that's added in the second step. The third step is esterification. So that would be adding this blue group that you see. This would be done by first using one of the reactants to break up anhydride. hydride will then be split, and then once it's split, it'll be attacked by this deprotonated OH, deprotonated by this the same bulky base as earlier. This would then do backside attack on this carbonyl, and then the electrons would then come back down and then kick off the nitrogen group, leaving you with an extra ester on your compound. Next would be hydroxyamination, which would be turning this group into an NHOH. That's done through this mechanism where the double bond is broken as this does backside attack, grabs a proton. Then later in the reaction, you can see that the protons are just intermolecularly rearranged, and then what you did here is reversed as you're taking the proton back and it's reforming the double bond. For the step 5, you'd be doing acetonitride deprotection. So this red group that we see would be getting undone. This is done through the addition of a weak acid. So this oxygen is protonated, makes it a better for holding more electrons. So these lone pairs get kicked up to the oxygen, breaks apart the ring. Water, our initial byproduct, does backside attack on this carbonyl, kicks it up. This does a intermolecular proton exchange, and then finally the lone pairs on the oxygen kick off the rest of the molecule, leaving you with the two OHs that you originally had.
The main method used was acetonide protection with the addition of sulfuric acid and acetone. This protective group was necessary to add to the method as it protects two adjacent alcohols and allows for acid-base reactions to occur without disturbing those alcohols. Thank you guys so much for listening to our presentation. I hope it was interesting and you guys learned a lot.